Hello, AP Physics team. Hope you enjoyed the cross products video. Now we're going to do our next set of videos on angular momentum and its conservation. So let's dive into it. As we're going through these, do stop and write down any questions you have. I know this is not an ideal situation, but you can email me those questions and I'll at least be around this weekend and I can send you any answers to anything that isn't making sense. So, angular momentum and its conservation. First, we're going to, I think it helps to just compare our angular or rotational momentum to translational. So we'll go translational and angular. Okay, when we were in translational or linear land, equation for angular momentum, P equals mv. Now, we already said that angular momentum, big L, so that is equal to our rotational equivalent of mass, which is moment of inertia, and angular velocity. Now, there are some other equations we can use for this. If we just look at I, we can break I down to mr squared, and omega v over r. So we can also express this in linear terms, even though this is an object that's rotating in some cases, spoiler alert. But then we can simplify this down to mvr, and that's the equation you'll see a lot of times. So mvr, you'll use that, or I omega, if you just have a point object that is moving with angular momentum, or if you're given unit vectors, we're going to take r cross with p, which we saw in the cross product notes. So we use that if we're given unit vectors. Okay, all of those equations, though, give you angular momentum. Okay, we're going to be using all of them, especially this I omega and mvr, just depending on what info we're given. All right, coming back here, translational. We know we talked about momentum being conserved when we did linear momentum, and how momentum is conserved when the net force of the system, so that's all the objects we're analyzing, is 0. Likewise, angular momentum is conserved if, same idea, just using rotational terms, so instead of net force, our net torque is 0. Okay, we're going to look at some equations going over here to, let's use 2 lines. For our net force, there's our FMA. And A is velocity over time. We're just deriving Newton's second law, m times v. Hey, that's p. So we can write Newton's second law. Actually, its original form is, so it's the rate of change of momentum over time. Same thing for angular, except it'll be our net torque. Okay, so it's the rate of change of its angular momentum over time. So that's an equation you might use. And we can go the other way too, and that our change in angular momentum, well, we can find our torque. Going the other way, that will be the integral of torque with respect to time. Okay, so that's that little table. Now, looking at angular momentum, so one of these variables is r, which You wouldn't think we'd have to revisit what r is, but believe it or not, we do. So r can mean the radius of rotation. So if we have an object moving in a circle with radius r, and it has a velocity, tangential velocity of whatever that is. Okay, angular velocity is going to be mvr. Crazy. If you're asked for the direction of the angular momentum, we can still use the right-hand rule. Okay, so for any cross product, we can use this right-hand rule. And so as you remember from cross products, so you point index finger in the direction of the radius, and remember radius always points outward from the center of rotation. So radius vector, and then line your kind of bent middle finger in the direction of your velocity vector, and then stick your tongue out. Not your tongue, your thumb. You can stick your tongue out too, though. So that's our direction of our angular momentum. It's coming out of the page. So you can still use right-hand rule for angular momentum. Just make sure, since it's r crossed with p, you've got to do your r first, and then the direction of v. Oh, yeah, because the momentum will be in the same direction of v because mass is scalar. Almost let that one trip me up. Okay, other way to find the direction. Pause. Sorry, I'm trying to figure out. Not the direction, the angle between the vectors. Okay, so I want to know the angle between these two. So say this velocity was, say it's going off like off a radius, and it's going off at that direction. So if r and v are not perpendicular, if they're perpendicular, you just use this equation. Ta-da. If they're not perpendicular, then we're going to have same equation, but just with torque, where we only care about the perpendicular component or the tangent component. Same idea here. So we're going to do sine. So if we put this vector over here, we're finding this angle. Okay, so this is our angle there. We want our perpendicular component, so that's why it's the sine. So that's our expanded version of that equation when it's not perpendicular to the radius. Okay, so why are we even specifying what r is? This is silly. Well, because an object doesn't have to be moving in a circle to have angular momentum. Okay, so and in that case, the radius, the distance of closest approach. Okay, what the heck does that mean? All right, so this is used when, so an object doesn't have to be rotating to have angular momentum. It just has to be moving kind of off of the axis or off of your reference plane. Okay, so I'm going to get stopped and we will pick up this problem in the next video.